Hi, I'm Ms. Risto, and I'll be going over the 3-2 notes with you. Okay, so we started talking about exponential and logistics, yes, on 3-1, and talked about the general formulas. Now we're going to apply those formulas to word problems. Okay, so you have your general formula, and I'm just going to kind of do some highlighting here. Let me get to the highlighter. Is you have, again, here is your general formula. Okay, now when we're looking at this general formula here, we are looking at A as our initial population, B is our rate, and X is going to be usually time. So now, just so you know, again, connect the two. When you're trying to find rate, these are how you do it. So if you have a growth, it's going to be, you need to do 100% plus your rate of growth, and if you have a decay, you need to do 100% minus your rate of growth. And in this case, 100%, since we're talking about it as a decimal, we are going to use it as 1. So growth is going to be 1 plus your percent as a decimal, and then decay will be 1 minus your percent as a decimal. So that's key. So make a note of that you have that. So let me give you an example of, just a quick example of how that would work. So you would have, let's say let me get to a, let's do blue. Okay, so we have initial population of 500. You have a rate of decay of 1.73%. And so I want to write an equation. So the first thing you need to do is you need to figure out your rate. So we're going to go ahead and do 1 minus 0.0173, because it's a decay, so I'm subtracting, so I'm going to go ahead and get that value. And then I write my function as my initial population, so 500, times our rate here, 27 to the x power. And like I said, x is usually in some sort of time with that. So that would be a model that we would use to answer additional questions on that example. Okay, so now most of these we're going to be doing in our calculator, so we're going to do our intersections and stuff like that. But you will also be asked to do regression functions. So we'll be having 2 regression functions. You'll have your exponential regression, which is in your calculator, is listed as this. So EXP regress, and it's kind of down towards the end. I think it is 0. I think that's what it is, and we'll look at it in our calculator. And you have a logistic regression, and the logistic is spelled out just like this, and this is going to be your B. I think so they're down a ways on your calculator. The thing to note about this is make sure you know your units. What year is your initial population starting in? What is your population being measured in? Like, is it in millions? Is it in thousands? Is it in hundreds? Stuff like that. So be aware of your units with this. Now, you do not have this example in your note packet, but it's just, again, an example. Whoops, I didn't clear this off. So in this case, we have a table here, and we are looking at the population of Arizona in millions. So again, so that means all of these here are listed in millions. So that would be like 3.7 million, 0.5 million. So just remember that these are millions. And the key part here is it's years after 1800. So that means that I would have to take each one of these. So like, for example, just kind of show you, I would have to take 1900 minus 1800. And that's how we would get 100, and so on. So these are the values that we would put in our L1. So instead of putting 1900, 1920, and so on, we would put it like this because of what year we started our population in. Okay, so the years would go in L1, the population would go in L2. Let me pull up my calculator here. So again, go to your stats. If you look on your edit, so here it is. So again, here are my years listed in years from 1800. And so now I'm going to do the exponential regression first. So let me go over to Calc. And like I said, exponential I think is 0, so it's going to be right after your natural log right here. right there. Yep, so there it is. And then hit enter just like you normally do. And hit calculate. So there is your A and your B value for your exponential. So again, so my B value or my rate is above 1, so this is growing. Our population has a growth rate. So now I'm going to do the same thing, and I'm going to show you exponential. So again, go over to stats, go to calculate, and again, it's down a ways. Now, one thing about exponential is it does take your calculator a little bit longer to get the regression function of exponential, and the main reason is because there's so many unknowns that you have that it has to find. So here's my logistic, and again, remember you're looking exactly for the word logistic, and you go ahead and hit, calculate this out. Oops, I must have missed that. Okay, so again, like I said, it's going to take a little while, so let's take a look at our, and especially if you have an older calculator, your older calculator is going to take much longer than you think. So just be patient, let it think its way through. So there it is. So again, you have your A value, and again, remember I mentioned that the calculator does give you the equation with the E. So here's your A value, your B value, and here's your limit of growth for that. So that's where you would find that in your calculator. Okay, so now let's take a look at some word problems. Now, we do not have the algebraic knowledge yet to do these algebraically, so we are going to do the first 3 examples graphically. We're going to come up with the equation, and then we're going to, to solve, we would put it into y1, y2. So, in this problem, so again, let's take a look at some keywords. We have a declining population, and it's declining at an annual rate of here. Okay, so that's key. Now, it does say it's in 1950, but the initial population or the only other population they're giving us is this, which this will become our initial population. So that will become our initial population, but we have to be key. It's after 1980, so that's going to be kind of our units for our time. So let's just write down some stuff that we know. We have, oops, let me get a different color so it's easier to see. So we have a starting population of 1,203,000, and then we have our X is going to be years after 1980, and then we need to figure out our rate or our B value. So again, it's a decline, so I'm going to do 1 minus 0.0144, which will come out to be, I calculated that out already, 0.9856. So then we go ahead and write our function. And again, using our starting. And then our B value or our rate to the X power. Okay, so that's just our initial equation. I kept my initial population written out in all the zeros and stuff like that. If you wanted to, you could change it to 1.203, but just remember it would be in millions. Since I wrote it all the way out, I have to write my 1 million all the way out. So again, I'm going to do 1 and then my 6 zeros here. So again, keep your units the same. 6 to the X. So now, at this point in time, you could divide and come up with a decimal. You don't have to, because we're going to, like I said, we're going to use this, we're going to solve this in our calculator. So we're going to put this into your Y1, this into your Y2, and find that intersection point. So again, remember, you are dealing with your X values are your years after 1980, so you might not need very big X values, because it might not take very long to go from 1.2 million to 1 million. But your Y values, remember the 1 million and Y1 is a horizontal line, so your Y max will have to be bigger than 1 million. It's declining, so it doesn't have to be much bigger, but you should have it at least to be 1.5 million, I would say. Okay, so go ahead, pause the video, see if you can come up with your answer. With that, let me change colors. Okay, so now hopefully you paused and found the answer. This is the answer I found, is 0.74. Now remember, this is 12 years after 1980, so to answer the question, you probably want to do 1980 plus 12.75, which comes out to be 1992.74. So the population would dip to below 1 million in the year 1992 with that. So that's why it's important to know your units. Okay, let's go ahead and go to the next example. Now in this one, the things that we know is, again, let me get my highlighter, is we have a half-life. So a half-life, that would mean our rate is 1/2. Okay, we have it says 5 grams present initially, so that's our initial value, our initial population, but this is the key thing here, it's 20 days. So my half-life occurs every 20 days, so that has to come into account into my equation. You have to make sure, again, that you know your units. So let's go ahead and write our equation. So we would have our is initial times 1/2, and now x, again, x represents units of time in our case, so we don't know how long, and so we have to make sure that since the half-life only occurs every 20 days, we are going to divide that by 20. So that would be that. So that's telling me by dividing it by 20, my x value is in days. If I didn't divide it by 20, then the x value would be in number of half-lives with it. So that's why it's important to know. You don't have to divide by 20, but just so you know that an x represents the number of half-lives. So again, we're going to go ahead and put 1 there. Have our equation. We're still going to use our calculator. Now after we do 3, we're going to be doing more of these algebraically. So again, start off, put this into your y1, put this into your y2, solve, and again, remember now you're dealing with smaller numbers, so go back and adjust your window. So your y maxes don't have to be very big, but your x number of days, remember a half-life occurs every 20 days. So that would mean, like, if we have 60, that would be 3 half-lives. If we have 100, that would be 5 half-lives. So since our x is in days, we probably want to go our x max to be like 50 at the minimum with that. So now we go ahead and graph, and you go ahead and do that, and I found the answer. So x is going to be 46.4 days. So it's going to get below 100 or below 1 gram in that number of days, or a little bit more than 2 half-lives. So it would take 2 half-lives for this to occur. Okay, so the next one is pretty simple. It's is giving you the formula. Again, just be aware of your units. So again, it says in miles above sea level. So you have your 4, which will be put into here. And then you're going to solve for h, which is right there. So again, you're going to go ahead and do 4 equals 114.7 times 0.5 h divided by 3.6. So again, do it in your calculator. You come up with an answer of h equaling 6.76 miles above sea level. And if you're not getting these answers or you're having trouble with your window, please ask when you come back with that, because again, this is all about being able to interpret your units, how to enter it into your calculator, and then explain what your answer is. Okay, this last problem is the only one that we are going to do algebraically. Okay, so this is, again, we're looking for a logistic. We're going to show all our work. So this is, again, the only one you're going to do algebraically in this. So again, show work. And you're going to use your algebra to do that. Okay, so now remember there are 2 forms of logistic formula. When you're asked to do this problem, you are going to use this form. You're going to use your c over 1 plus a times b to the x. Again, if you do the regression function in your calculator will give you the base E form. But this is the one you use if you're doing your algebra. So again, we have three unknowns. We have a C, A, and a B. So we need to have three things to help us find those those three unknowns. And we do have them. We have initial value, which is going to be written as 0, 12, which is like your y-intercept. We have your limit of growth, which again is your C value. And then we have this other point that the graph goes through. So those are our three things that will help us solve for our three unknowns. So let's go ahead and start by just writing the equation with our limit of growth. So I'm going to go ahead and do it in red. So we have our function equals 60 over 1 plus a times b to the x. Okay, so that's your starting point. Now the next thing, so we've used this one. Well, let me go back and use that. So we use this one, so we're done with our C. Next step is we're going to use our initial value. Now remember, this is not your A value. You have to solve for A. So that's your next step, is you're going to solve for A. Okay, so again, we have, this is our X and our Y, so I'm going to plug those in. So we have 12 equals 60 over 1 plus a times b to the 0. Again, remember, anything to the 0 power becomes 1, so this kind of drops out. So now we have 12 equals 60 over 1 plus a. Okay, and now it's just as solving for a. So I'm going to go ahead and cross multiply. So I'm going to put this over 1, and so that means I end up with 12 plus 12a equals 60. 12a equals 48. So a is going to equal 4. So that's my next step. So again, I'm done with this one. And so the only one I have left to find is B. So now I'm going to go ahead and I'm going to use this point and my new A, and I'm going to plug them into my equation to find my B. So again, remember, this is X and this is Y. So we have 24 equals 60 over 1 plus 4 times B to the first. Okay. Again, remember, these are not like terms, so you can't add these together to get 5. You got to keep them like that. So again, now you're going to go ahead and solve for B. So we end up with 60 equals 24 plus 96b. And so let me see. So we end up, subtract by 24, we end up with 36 equals 96b. Divide by 96. And so we end up with a decimal, in this case, of 0.375, equal to B. Okay, so now we can finish up. Again, write the equation. We already have our C value. We have our B. We have our A. So let's just go ahead and rewrite our equation using our those values for our unknowns. So our function is going to equal 60 over 1 plus 4 times 0.375 to the x. So this would be our logistic equation that fits all three of these criteria up here. Okay. So again, let us know if you have any questions. Have a good break, and we will see you when you get back, when everyone gets back.